morning to all. Welcome back to fourth day of this
cooperative spectrum sensing and compressed spectrum sensing. So let me share the screen now, and I have, and Dr. Kiran, I think you have to give me the co-host permission.
Yes, sir. Kiran madam, please give co-host to Neelakandan sir.
yes, yes. 1 minute. I am checking that. 1 minute.
Yeah, sure. Okay. So for better transmission, let me turn off my video so that you'll be able to. Yeah.
Yes, sir. Thank you.
Okay, so today let us discuss the spectrum sensing for fading channels. And actually this talk I have split into two. One is that let us see the first some basic concepts behind the spectrum sensing and how does it help and where we apply that and what all the techniques we have for the spectrum sensing and so on. So, and this slide, the PowerPoint is more self-explanatory. So I will go to certain extent and I would go slightly in a faster pace as and when necessary because the slides are pretty much with figures, illustrative figures, and where you can understand from yourself, even though if I skip some of the slides. Nonetheless, the second part, I mean, where we have to check the compressed sensing part, how it is applied in the spectrum sensing concept. That involves more mathematical details, slightly. So I would like to pitch more on that. So let me go to some extent with these slides, and then I will go back to the other slide, where I can spend some time on that as well. So that it would cover both the wider audience, where everyone can understand the slides in the PowerPoint, and that in the second part where we have some mathematical details that would give some research directions those who are working in this area of wireless communications, and maybe some of the projects can be floated for your UG and PG students. And this is one interesting line of thought. We can shed light on it. Okay, first let us see why we have to think about this cognitive radio and what is the motivation behind that. So now we have the one side we have the scarcity in the spectrum, and on the other side there is a lot of spectrum which is being underutilized. So this kind of dilemma actually giving the motivation to us whether we are effectively using the spectrum or not. So there has been a wide interest to take the spectrum auction and how do we communicate and which band I have to choose. So there are several things which working on that, but nevertheless the point is that many of the spectrum is not effectively used in the sense that suppose if I allocate the user particular channel, the channel is not completely occupied by the user for the whole duration. Say for example, if I have to give you some motivation behind that, when the human voice is sampled and then taken for the communication in the TDMA mode generally, so your mobile vocoder that samples the signal, and what happens when we speak, we make a lot of pause between the words and as well as between the syllables. That pause is approximately in the order of milliseconds. So if they nicely segregate all the millisecond and make use of other control channels, that spectrum can be used. So these things are being taken care slowly one by one when we have the advanced vocoders and so on. But the similar line of thought has been shed on this overall spectrum as well. For example, if you look at this figure, so that is showing from 0 to 6 gigahertz, where most of our communication, including our terrestrial, cellular, and defense communication, everything happens. Nevertheless, we have the licensed band as well for the military communication, but essentially this is for the overall band where we have been communicating. But if you look at the spectrum sharing from the spectrum sharing information, you can get this information, occupancy information from that, where you can see most of the spectrum is occupied only at the lower level. And even below the 6 gigahertz, what we call it, refer to as sub 6 gigahertz, there too, many of the spectrum is not properly utilized. There is a vast underutilization area in the region in this spectrum. Of course, if you go to the higher frequency beyond 6 gigahertz, and if you go as we have seen yesterday, where the millimeter wave is being proposed, there we have a lot of vast spectrum, but the problem is that the technology, like whether we have the right technology to make use of that or not. But this problem is opposite. We are not looking for the vast higher order spectrum. Even in the sub gigahertz, what we are using, are we using that effectively? That's what the question now. So here, the cognitive radio is a technique which is addressing the problem that even below the 6 gigahertz, how to make it effectively make use of it. That is what the question. On the contrary to the millimeter wave, where you think about how to make use of the very high frequency spectrum, what are the technologies that potentially that can support you to do that. But here, the concept is, or the idea behind the learning this topic is to how to make use of the spectrum effective in the actual band where we are using now. And if you check the maximum amplitude of the spectrum in the power spectral density, frequency versus amplitude in dBm, so they have segregated heavy use and the sparse use and the medium use. So this is how they check out the spectrum, how it is being used. So now the question is that, can we do something in the region of medium use and sparse use to improve the efficiency and how to make it better utilization factor, right? If you think of a time and power occupancy in any spectrum, you can think of a three-dimensional figure. So across each time, what are all the power level transmitted with different frequency. So for example, here this is a gap. There is a coverage hole or spectrum hole. And here you have another spectrum hole and so on. So we have to think of the figure as a three-dimensional structure with the tiles. And our objective is to just hop over the holes and reach it. That's it. So across the time, we think of several holes. Just I take this spectrum now. Next time, this is occupied. So I have to hop over here and then come here and like that. So just think of a person who is jumping over the tiles, like wherever it is empty. So now the objective is to, across the time in the frequency band, you have to check where the power level is minimum so that you can communicate without any interference. At the same time, whenever the primary user comes, let me call it as a primary user, because they have been using the spectrum, they have the priority. That's why they are the primary user. Whenever they are not using, how to make use of that from the secondary user side. So this is the idea behind the spectrum sensing. So essentially all that you have to do is you have to measure the power in the particular band and you have to decide whether to communicate in the band or not. So typically this involves a cycle of activities. You have the radio spectrum, you have to sense that, then you have to decide whether you can communicate in that band or not, then you have to act on the decision. So this is like a cycle of events, what we do in general. The flow diagram of what is happening in the receiver is, we have the received signal, you apply some spectrum sensing technique, you compare with the threshold. So the threshold tells you that whether the band is occupied or not. In other words, whether you can communicate in the band or not. If the band is not occupied, you can go ahead and use it and make a decision on your sensing, right? And in broader case, the spectrum sensing can be divided into two major classification. One is cooperative spectrum sensing, another one is non-cooperative spectrum sensing. In the non-cooperation case, every user is independent. It has to think, it has to decide, it has to act. So no one else is going to interfere or help in that part. On the other hand, cooperative spectrum sensing, that further divided into two categories. One is distributed sensing, another one is centralized sensing. As the name implies, the distributed sensing is like the power, the control and decision making autonomy is given to all the users. In the sense, centralized sensing, of course, by just our common sense says, every decision is made at a centralized point. Apart from that, so this is on the spectrum sensing, what we call it as a methodology or the way of the spectrum sensing. But how do you sense the spectrum? That technique for spectrum sensing, that there are several ways of doing that. See, this classification is about the methodology or modality of spectrum sensing. This is about the technique for spectrum sensing. Suppose if you say that one user is sensing the spectrum, how does he do? That's what the question about. First, there are several ways of doing that. All of them can be categorized into four major pillars. Like one is on energy detection, another is based on autocorrelation based detection, and next master filter based detection, and including distance based detection. And we have several other heuristic approaches where we have wavelet based technique or compressed sensing and so on. But essentially, all of them is depending on any one of these major factors or a way of measuring out of these four techniques. But now we will see one after the another and get some basic idea about how these techniques work. And then we will see the challenges in the technique. Then we will come up on the compressed sensing spectrum, where that framework helps to do the spectrum sensing part. First, let us see what is this energy detection part. So I'm just going to have a glimpse of all these four different techniques. How do they work? Block diagram will be very simple. I will come to the challenges, how to do that. If we have to do the energy detection based sensing technique, you just have the received sample y of n, take to analog to digital converter, right? Then actually this is y of t and you will get y of n, of course. Then take the Fourier transform and take the square of it. So there are two things. When you have to measure the power spectral density, when you have, I think you might have seen the PSD expression two different ways. One is the Fourier transform of the autocorrelation. Another one is that magnitude of the Fourier transform square. Both of them will give you the power, but which one has to apply where? If we have a random signal, then you have to apply the autocorrelation based spectrum estimation. And if you have deterministic signal, where you apply the Fourier transform, you can take the Fourier transform and make the square. So we apply both of these technique. First one is energy detection based on the Fourier transform square. Actually, what generally FFT will do, I'm not going to in depth about the mathematics, but if I have to tell you intuitively what is doing, if you take an endpoint FFT within a band, okay, actually what it is doing, suppose you have a signal, you sample with the rate fs and then take endpoint FFT, okay, then it makes a bin or frequency band whose width equal to fs by n, and the each value, the coefficient x of k for k is equal to 0 to n minus 1, that is giving you the energy in the 0th band, first band, second band, and so on. And each band width is equal to fs by n. You get the point? So what it will do, let me repeat the point. Say suppose, let me take this figure for convenience. Say 1, 2, 3, 4, 5 blocks are there. Say I take 5 point FFT. So this is each of the width equal to fs by 5, where fs is a sampling frequency. And the 5 coefficients, x of 0, x of 1, x of 2, x of 3, x of 4, each one corresponding to magnitude square or else the energy in the particular band. Okay, that is how FFT works. And that is the reason, for example, if you think of the DTFT to discrete time Fourier transform to fast Fourier transform. Fast Fourier transform is just an algorithm, that's an implementation. Actually, that is discrete Fourier transform. So you have two things. One is DTFT, another one is DFT. DFT is the samples of DTFT. Isn't it? DTFT you represent as x of e power j omega, and DFT is of k, where k is equal to 0 to n minus 1 is n equally spaced samples from the continuous function of x of omega. I hope you can visualize what I am saying. Right? So what will happen? The n determines the resolution of the spectrum. How far your band, which, for example, fs by n is the width of this band. So that n determines the resolution and as well as sampling frequency. So if you have to make a finer resolution, meaning that suppose I tell you one statement. In 1 megahertz band, say 10 to 11 megahertz, the energy level is say 5 joule, for example. Would you accept this statement, or would you be happy if I say that from 10 kilohertz to 11 kilohertz, occupancy level is say 5? Which one looks better? The second one, because I am telling you very minute details in the kilohertz level. But if you have to have a higher resolution, either you have to increase sampling frequency fs. Fs increasing means your A to D is working faster. So overall resolution of this matter determines how fast the clock works here, this entry point. Is my point clear? So if you take an FFT, if you have to have a finer estimate of the spectrum, you have to go for higher sampling frequency, higher and higher sampling frequency, right? I will come to that point later again. Just I want, other blocks are quite trivial. I don't need to explain much about that, but you should, I wanted to tell you what exactly the problem in this kind of methods, right? And this is similar to the Euclidean distance, where we think of the signal as a random, either we interpret that as a random signal and apply some autocorrelation function. We have a reference line that is like a threshold line, and then compute the Euclidean distance with the reference matching, and then do the sensing decision there. And in the case of again wavelet, all these techniques are, the concept is same, only what kind of transformation you apply. There you apply the Fourier transform, here we apply the wavelet transform. I hope many of you might have come across the wavelet transform either in image processing or in some other context. Essentially, Fourier transform is trying to decompose the signal into multiple sinusoidal components. Every atom or every minuscule amount of that equal to one frequency sinusoid. But in the wavelet, we are trying to decompose the signal into several wavelets. So where you can control the wavelet in time and frequency. So if I have to quickly summarize the difference from Fourier to wavelet is that in the Fourier transform, say for example, suppose I have given you a signal, you can apply the Fourier transform, you have the spectrum, right? Now the spectrum, for example, the spectrum tells you that there is one component 10, another component 12, say for example. The Fourier transform can tell you what are all the frequency component present in the signal. Suppose think of two time domain signals. One has the sum of 10 plus 12 component. Another signal, frequency component 10 comes first, 12 comes later. You think of these two different signals. One has the superposition of two component. Another signal has frequency 10 comes first, it stops, frequency 12 comes then, for instance. If you apply the Fourier transform, both of them will have the same spectrum, isn't it? So the Fourier transform spectrum does not give you the time information. It tells you what are all the frequency component present, but that doesn't tell you when they come. So that is why we go for the short time Fourier transform, where you just take a small portion of it and you just cut and frame by frame or block by block you apply the Fourier transform, which is referred to as the short time Fourier transform. And again, when you have a block, Heisenberg uncertainty principle comes into picture, whether you have to take the block larger or smaller. So that is uncertainty behave between the frequency and time. So you cannot have a better resolution in both time and frequency. So to control over better about the time and frequency slot, we go for the wavelet transform. Okay. Anyway, all these details will take us into signal processing side. Just I wanted to tell you the difference between Fourier transform and wavelet transformations. Right? And again, matched filter, of course, the term implies. Matched filter is nothing but you have a copy of it, you just match it to that and see. So matched filter can be implemented in a convolution filter. I hope you might have come across matched filter in several occasions in the digital communications. Essentially, matched filter is for given a signal, say you want to detect that. So you design a filter whose impulse response equal to or whose impulse response is matched to that particular incoming signal. What is meant by matched? You just flip it and shift it by a factor of t. That is how it is matched. If you have such a filter whose impulse response equal to matching to that input signal, that would maximize the SNR at the output. That is the purpose of the matched filter. Of course, other things are quite trivial. The convolution block is there to emphasize that matched filter can be implemented as an LTI filter. Right there. So these are the different techniques. How do we, what do we apply for sensing the spectrum, make a decision whether there is a spectrum occupancy or not. Anyway, I have a lot of things to come back to that point. Let me take the other points on the periphery and then come back to the core there. For example, if we have a spectrum frequency and power level, there are several legacy users or primary users, and wherever there is a core, the secondary user can make use of it. That is for the opportunistic spectrum or cognitive radio. So what we are doing, we have wide spectrum from say 0 to 6 gigahertz, for example, and say for example 4 to 6 gigahertz. So in that band, legacy primary user will be making use of the spectrum, But meanwhile, wherever the spectrum is free, you can occupy that. But this is not constant, right? One user may communicate here, then he may stop, he may come here. Another user may come in this band. So you don't know when the primary user will come and when the primary user will occupy the spectrum. Okay, I hope you have some background about cognitive radio. That's why I'm telling only at the surface level. Essentially, the cognitive radio is that you have a spectrum. They are the licensed primary users, okay, whom we refer to as legacy user. Now, we have come to know that the spectrum is completely underutilized. So we are introducing the secondary users where they are not supposed to disturb the primary user. As and when there is a gap or there is a hole in the spectrum or there is an occupancy, non-occupancy in the spectrum, we can go and communicate in that band. So what they have to do, they have to keep on sensing the spectrum every now and then whenever they want to communicate and occupy the band what is free. And moreover, once they have occupied a particular band, say for example, there is one cognitive radio user who is a secondary user. He knows that this band is free, so he started to communicate here. He cannot keep on communicating the same band until his communication takes over. No, because suddenly another primary user can come into this picture to occupy this band. So the secondary user has not only to communicate, also it has to do that, keep on sensing the spectrum continuously, whether primary user is any of the primary user is coming to occupy that or not. So it has to do two jobs. One, first you sense and detect that it is free. If it is free, you communicate, but also keep on checking whether primary user is coming there or not. If he is coming, he has to release the spectrum immediately without causing any problem or disturbance to the primary user. So while communicating itself, that has to do the sensing part. So sensing is not the only job at the beginning. Sensing is a continuous job. It has to keep on sensing to determine whether it is free, and also it has to determine whether another primary user is coming to the band or not. So now every secondary user frame will have one sensing part, another is a payload part where the data can be transmitted. So faster you come to a conclusion or decision whether to communicate or not, remaining time you can use it for the transmission. So that is up to you. But at the same time, you are not supposed to make any false alarm, meaning that there is no primary user, you think there is a primary user and leave it. That makes you inefficient. At the same time, you are not supposed to miss in the sense that there is a primary user, but you think there is no one is communicating. I have a question, I think. Was there any question? I don't know. Okay. Right. Then, so what are the essential problems for the cognitive radio? Finding the holes in the spectrum, allocate the open spectrum, and then you have to transmit from adjusted to occupy the minimum bandwidth. For example, you might have seen the, if I have to tell you a better example, what we are using the GSM is a kind of a GMSK filter, meaning that you have to shape your waveform such a way that that is not having much out of band radiation. We have to minimize out of band radiation. So how to shape your waveform? That is what would help you to restrict your spectrum within a particular band. Okay, so that is what it says, waveform adaptation. And of course, dynamic resource allocation, that's what I discussed now. Okay, now let us come back to the original theme of the problem. So far we have said we have wideband, we have a lot of techniques proposed, whether energy based or correlation, whatever it is, right? Now the question is that you are going to get the samples right. From which band you are going to take the sample? In the sense that suppose you have to sense a 6, say for example 10 gigahertz band, or say 100 megahertz band, for example. Let me take a reasonable amount. You have to sense 100 megahertz bandwidth, okay? And wherever it is free, you can make use of it. I give you two options. One, get the whole signal into that 100 megahertz bandwidth, put a big band pass filter, and add low noise amplifier, mixer, and so on, blah, blah, all the RF chain circuits, and do the analog to digital converter, and compute the Fourier wideband sensing technique. You can apply whatever you want here. Either Fourier transform, wavelet transform, whatever it is. You apply the technique here and come to a conclusion. Since you are taking the whole 100 megahertz bandwidth, the output is expected to have, say, 0 to 100 megahertz. What are all the bandwidth free? So that is what the output here. This is one option. Second option, you keep multiple 1 megahertz bandwidth, 0 to 1, 1 to 2, 2 to 3, 9 to 10, and so on like that. For each band, you apply all the R option technique, finally make a decision whether this band is occupied or not. Right? Correct. So this is giving you all result in single shot. This is giving you for every band separately, whether this is occupied or not. This is occupied or not. Now, what are the pros and cons of these two techniques? Here, you need multiple RF chain. Okay, more and more you want resolution, you have to make a smaller band pass filter here. More you go for smaller band pass filter, higher the number of RF chains, right? But these things are not, as I already said, told you yesterday that the most power hungry, the expensive part in the communication system is RF chain, right? So that requires so many RF chains, which consist of the low loss amplifier, mixer, oscillator, automatic gain controller, ADC, DAC. These are all, this is, the whole chain is called RF chain. Okay. Now, of course, that is a fixed band. Okay. What is the problem? Let me tell you one example. Suppose you occupy 0 to 1 here. This is 1 to 2. Okay. That is what we, okay. So this chain will give you the result here, whether 0 to 1 is free or not. This chain will give you the result whether 1 to 2 is free or not. Okay. Now, suppose a particular user is communicating from 0.5 to 1.5. So then what will happen? This also will give yes, this also will give yes. So automatically you will skip both the band. Again, you are coming in effective manner. You get my point. So even though it is actually occupying 1 megahertz bandwidth, you are thinking that 2 megahertz bandwidths are occupied because you are making a fixed band. These filters are not variable. You check for 0 to 1 and you check for 1 to 2, but you are not adapting that. So if a particular user is occupying from 0.5 to 1.5, that will induce the spectrum decision both here and here, which is again ineffective. So that is a problem in the fixed band. But of course, if at all you think to make it adaptive band, that's again more complex circuit. Making a tunable band pass filter at high frequency is really challenging again, right? Next. And again, what is energy direction within each band pass filter? Again, you have to do all the computation in each of these band pass filters, right? Okay, why should not they go for a single short estimate? A single RF chain, yeah, very beneficial. Flexible to dynamic power spectral density, yes, because whenever the user is going from 0.5 to 2.5 or wherever it is, essentially the output is a full sketch, full signature of the spectrum. So whatever happens, that will give you the output. So you don't need to worry about the fixed band problem in this case. What is a major challenging part here is this part, analog to digital converter. If at all you have to operate at the very high frequency, you know the Nyquist sampling rate, right? The sampling speed must be equal to twice the bandwidth. So you must be able to have such a very sampling circuit, FS, at the front end. So that is the biggest challenge in that. But designing such a high speed, the ADC, DAC is not that much easier. Okay, so that is why directly estimating the wideband sensing in the one single shot with the whole band is extremely challenging task. Okay, now this has its own challenges. This problem has its own challenges. Then what should I do? That is why we think of different techniques, how to accommodate all the problem. Like a hybrid mode, you take a wider band and then do some processing, and after the estimate, you go for the particularly interested narrow band and then do the estimate. So you can think of so many heuristic and some kind of noble thoughts on that. That is the problem now. Okay, so this is the starting level where the problem occurs. As to summarize that, suppose if you have to see your cognitive radio has to sense a primary user signal, even as low as minus 104 dBm. This is what the standard specifies. See, minus 100 dBm is what I would say. Typically, we communicate in the case of minus 5 to 10, even our nominal communication. Minus 100 dBm is very, very low. But even you have to identify those primary user and you have to release the spectrum once it starts to communicate. So what are the technical challenges? Sensing at the low SNR. Okay. Second part, modulation and classification. So what kind of modulation is better for that? And you have to shorter the sensing time, because more you make it shorter, better you can use for your communication of the data. And the robustness against the noise uncertainty. And because in the wider band noise, we don't have much deal about the noise part. You have to live with it. And you have to, another problem is interference among the user itself. So how to mitigate that? So now we have finally another problem is that how to accomplish signal processing at even such a low SNR value. So problem one, how to make use of the complexity or the resolution trade-off. Second part, how to accomplish the signal processing at the low SNR, right? So what are the proposed solution for these problems? One is that go for compressor sensing with a wideband, applying the sub-Nyquist straight sampling technique. Okay, there you can get rid of the compressor sampling based framework. The term compressive sensing is something new to many of you. I have a separate slide for you to explain. So that is why I'm slightly bit faster here so that I can spend some time on the mathematical part. And there is another feature in the wideband signal, which is known as cyclic feature. I will come to that part in the slide, cyclostationary part. So where you are exploiting the sparsity, as I already told you that sparsity is nothing but when you, whatever you think of. Say if you think of a vector in the wideband, vector in a large dimension, 100 size vector, say there are only 5 non-zero entry. So the vector is sparse. If you have a very wide band, it is sparse means it has a very wide bandwidth, but the occupancy is somewhere here and there. So that is called sparsity, very less occupancy, opposite of the dense, that's all. Now, based on all the problem, people have started to think about that. Definitely we cannot go for the fixed band, but at the same time, I cannot simply go for the wide band because of all the challenges what we have discussed. So I have to work in a kind of a hybrid mode. To do that, let me take the wideband signal itself. But is there any way for me, any mathematical framework that can help me to do the sub-Nyquist straight sampling? Because one of the major challenges that was posed for the wideband sensing directly was that the sampling frequency. Because if we have to measure 100 megahertz bandwidth, you have to sample at least at the rate of 200 samples, mega samples per second. So the question is, can I adjust it? Can I reduce that? So that is what one question. Another part, not only the sparsity, the spectrum, the wideband signal also has another property which is known as cyclostationarity. I will explain in the subsequent slide. So can we combine and make use of these two advantages simultaneously and get something done? So that is what the idea of the proposed solution. Okay, so some thought on the sampling rate. Probably many of you might be aware of the Nyquist rate and what is the challenges in the Nyquist rate and so on. Now, when you think of the wideband signal, the Nyquist rate is very high. So what can we do? Go for the compressor sensing part. Okay, this basic I will come in the separate slide, but anyway, just I have, these slides are given in the very layman terms like anyone can understand, though you are not working in this area. But I will come to the details in the other slide. Just I skip it and I come to the cyclostationarity part. See, any modulated signal is cyclostationary in nature. What is meant by cyclostationarity is that suppose say you have a signal, you cut it with the part of T0, okay, and you compute the autocorrelation. Autocorrelation meaning that you compute the matching between the waveforms or portions of width equal to T0. If you think of such a operation, then that will give you the cyclostationarity feature in the signal. Any modulated bandpass signal has a cyclostationarity feature. Let me go to the slide and explain you better in this case. I will come to this slide slightly after telling you this part. Suppose, say for example, you have one pure cosinusoidal wave. Okay. So now this theta, if it is varying, that is angle modulated signal. If it is varying here, amplitude modulated signal. What you are doing, just you compute only the average of it, say minus t by 2 to t by 2. The mx of alpha tells you that the corresponding component in that alpha. Okay, so if you put alpha is equal to 0, that is pure DC component. That will give you the estimate of the DC signal. And if you go for higher frequency, that will give you the higher frequency component. Okay. Now, after computation of that, let us see, for example, suppose you have the full signal like that. Just imagine you cut like this with the portions equal to T0 and paste it here. That is equivalent to folding with the width of equal to T0. So you have 0 to T0, T0 to 2 T0, and so on. So that is what I have copied here. Now sum all these signals and compute the average. That is what this operation. If you do that, that is equivalent to, I'm just keeping the mathematical details. If you do that, this is what the details begin the mathematics. If you comfortable, you can look at it later. That is equivalent to passing that through a band pass filter. The operation what I have told you is equivalent to that. If you control the width of the signal, that is equivalent to passing the signal through different band pass filters. That is what the idea is. So suppose if you have to pass it through a band pass filter of say 0 to 1 megahertz, you take a particular value of T0 and do the operation. No. I want to compute say 0 to 3 megahertz, have another value of T0, do the processing. So by changing the value of T0 with which you are computing the autocorrelation, that is equivalent to passing the signal with the different band pass filters. By doing that, what actually you are getting? Let me show you one thing. Now let me come back to this part. Suppose if we have BPSK signal, okay, if you take the Fourier transform of it, what you will see? The same BPSK signal, you do the operation here, and if you check it out, for this is one frequency f, this alpha is a parameter. I have mentioned that in this slide here. This part. Essentially, by varying the f and alpha, that will give you different lobes, sync lobe at different part of the spectrum. This is like a signature of the waveform. In other words, this is called spectral correlation density. This spectral correlation density is unique to every bandpass signal. Let me repeat the point clearly. If you compute, whatever the computation is, if you compute the spectral correlation density, that will tell you the type of modulation a particular signal has and the type of energy occupancy in the particular signal. For instance, if you come back to, I show the figures rather than the mathematical details. Yeah. After computing the SCD, if you plot it like a Fourier transform, say for example, then every type of modulation will create different type of signatures like that. So that is the idea of it. From this pattern, these diamond patterns, you will be able to identify what kind of modulation, what kind of signal that is. Every signal has its own spectrum pattern like that. From the pattern, you can identify what kind of signal this is. For example, for different values of M and N, without worrying that what is M and N, I will tell you what is this. Just you have say two parameters M and N. These two parameters is controlling 1, 2 in the X and Y axis of the map. So different signal have different occupancy level. For instance, if we have this 1, 2, 3, 4, like this one, that corresponds to say for example a BPSK signal. Another QPSK pattern that will induce this 2, 1, 3, 4 like that. So out of the tile diamond structure all through the two-dimensional platform, by controlling the M and N, you will be able to identify what kind of modulation that signal has. This is one feature of sensing the spectrum. That is why we go for all the blocks in this part. First you have the original signal, multiple signals are coming into that. We apply the compressor sampling theorem, which we will be learning later. From the sampled and recovered signal, you apply the cyclic spectrum reconstruction technique. So this part will tell you what is the fingerprint that signal has. From that fingerprint, you will be able to identify the type of modulation, the occupancy level, and everything. From that, you can decide whether the band is occupied or not. This is one another estimating the spectrum, in the sense that anyway, when the primary user or anyone is communicating, he has to do with any kind of modulation format, which is typically available. Can we use out the property from the modulated signal and how the modulated signal spectral correlation density behaves? Can we do something with that? That is what the second part of this idea. And the first part is that now again, how to get the overall band signal in the wider bandwidth and do the processing. So before coming to this one, you have to capture all the signal in the wider band and do the computation. Then only you can give it to the cyclic spectrum estimation. So this is a primary channel and this is secondary part. In the primary part will come in the other slide. The secondary part essentially, just you have a signal, if you do the SCD, the spectral correlation density, and plot it, that will create a unique fingerprint for every modulated signal. That is what the essential statement. From the signature, you will be able to identify what kind of modulation it has, what kind of spectral occupancy that has. Every information can be captured by estimating the cyclostationarity of the modulated signal. Okay. And I think I just skip these mathematical details. Have a look at it if at all you are working in this area. Another part, another aspect of the spectrum sensing is that cooperative spectrum sensing. As we have already discussed, we have several nodes, relays, everything here. Can I make use of the several nodes, some cooperation among the, rather than independently every cognitive user estimating the spectrum, can I come up with some kind of a joint approach? That is what the cooperative spectrum sensing. So the reason we are going for that is the detection part of the spectrum sensing is often compromised by various factors like multipath fading and lack of channel quality information and poor SINR. All these things lead to the secondary user either to underestimate the spectrum or overestimate the spectrum, like a false alarm or probability of miss. These both happens because of all this nature of the wireless channels. So one proposed solution is that cooperative spectrum sensing. What is that? Suppose, let us say one example in this case. This is a primary network and there is one another overlaid cognitive of it. Okay. Now the primary user is coming. Primary transmitter is coming. Now the role of this CR2 cognitive radios are they have to estimate the spectrum. They have to estimate the spectrum and decide whether it is free or not. And from that has to come to a conclusion whether to transmit in the band or not. Right. If at all that has to estimate the spectrum, that should get access to the primary user signal, right? For example, this CR2 is directly, even though it is in the coverage of the primary transmitter, because of the shadowing effect from the house or a tall building, that is blocking the signal from the line of sight. So it is just only getting the reflected or scattered signal copies of from this another building. Whenever the signal is being scattered, that is leading to multipath fading or shadow. Because of the effect, the CR2 will not be able to effectively or efficiently estimate the primary user signal. So what it will do, it will think that that particular band is free and will start to communicate. Automatically that will create an interference to the primary user, which is directly receiving the signal. Because it doesn't know that that particular band is occupied. Another reason is that CR3, this is completely away from the coverage area of the primary user. So that may think that another band is free and it will communicate. That will also create interference to the primary user. So like that, there are various reasons why we have to take these challenges of kind of a cooperative spectrum sensing. That is, you have the spatially distributed users. So why don't you all of them share the information among each other? For example, if these CR1, 2, 3 communicate among each other, and if they come to decide based on that, then definitely CR1 knows better about the transmitter than CR2 and CR3. So like that, we are trying to create the pool of information from the spatially distributed users. And of course, that will improve the detection performance compared to the single user's independent detection. Right? But the problem is that the sensing delay. Since all of the users have to sense and then report either to a centralized part or in the distributed way, the time for sensing and coming to a conclusion is increased. Whenever your team size is larger, obviously decision making will go longer. But if at all you can come up with a method with like a quicker detection, you have a larger time for the transmission of the secondary user. This is what one important point. You have to reduce the time for sensing the signal. Then the remaining portion of the time you can make it for the transmission. And one way of the cooperation sensing is that, say for example, if you think of the noise floor because of multipath fading and the path loss, if you think of these two as a wall that is a barrier for the cognitive user performance, from the cooperation you can come out of the wall to some extent. So this cooperation can help you to overcome the barrier or noise floor to a certain extent where you can do some signal processing to overcome the effect. And what are the types of the cooperative sensing is, as we have already said, centralized or distributed or relay assisted. Let me show you one picture of it. In the case of centralized, you get different cognitive radios. All of them are connected to the central pool, where every cognitive user decides on something and reporting the decision to the central fusion center. There the decision is made whether the particular band is occupied or not. So again, that will communicate back to all the users, other cognitive users. But of course, you can immediately say that time delay will increase because everything has to sense and report it. And again, that has to do the process and send it back to all the cognitive users. On the other hand, every user can come up with its own decision with the information from the other user. For example, CR1 will estimate and simply that will pass the information to all other users. Like that, every user is communicating to all other users about their decisions. So everyone can make of their own decision. That is a distributed way of sensing. And another one quite interesting way is the relay assisted sensing. For example, suppose there is, see, the first and third figure are same, except there is only one difference is that here it is assumed that all the cognitive users can directly connect to the central fusion center. But here there may be cases even that CR1 and the central fusion center may be far apart where it cannot directly communicate. So just it is using another cognitive radio which is close to that as a relay to that. So it will pass to here, this will pass to here. So this is the only difference between centralized and relay assisted. For example, here in the centralized, if CR5 is not able to reach the fusion center, that cannot do anything. But in this case, that can pass information to CR4 and CR4 can communicate to this one. Don't look at the figure in the scaled way, like both of them are in the radial distance. Just I have put for the example case. Right. I think I have, yes, I have maybe another 20 minutes, 25 minutes. Let me, I just leave the other slides to you, which are quite self-explanatory and with illustrative figures. Let me go to the other part and where we have the very important theme of the spectrum sensing in the compressed sensing part. So let me stop sharing the screen and go to that. I have to spend some time on that. Yeah. Okay, so let me just, what are the different types of fading channels? That is what given in here. So this is the, for example, what is a path loss? What is shadowing? What is multipath shadowing? All the effects are plotted in this figure. The fading generally means that if you have more than one path, so that is called fading, like fluctuation of the signal, whether in the large scale fading or small scale fading, like that tells you that the random fluctuation of the received signal. For example, if you look at it, there is a thick dot line and another one is a smaller variation on this. This is called like a large scale fading and a small scale fading where it is happening in the minute level. Okay. And what are the different types of propagation model? In the case of ground wave propagation model, the atmosphere behaves like bending the signal towards one transmitter to receiver. This is like the refraction effect of the electromagnetic waves. And hope, I think many of you might know the mirage, which we typically see during the summertime, where we have the some illusion about the water. That is like a bend of a signal. Suppose you have one image or car standing here, because of the different layers in the atmosphere due to heat, the light actually bending towards another user. But when you are seeing from here, actually our human eye cannot perceive the bend of a signal. So that will imagine that is coming directly from space. So you have one car and image of it below. That is what we think it as like some bodies there. Similarly, any layer with the different atmosphere and different intensity level that will bend the electromagnetic signal. So that is a principle behind the ground wave propagation model. We are just bending the signal along the curvature of the ground. And what are all the frequency level that is suitable for? I have mentioned that here. And again, as I said, the ionosphere that is behaving like a reflector or in a certain frequency. So you can make like a totally internal reflection, how the light propagate in the fiber So like that, some band, like in a particular band, the electromagnetic signals can be guided with the ground and the ionosphere. These two behave as the guiding way pattern for the electromagnetic signal and make it traverse through one transmitter to another. And of course, line of sight, what we typically use for the terrestrial and cellular communications, where the towers are in the direct vicinity of each other. And I have given several models of that. This is what one of the model yesterday I was discussing. Suppose if you are just standing in front of a tower, you will get on direct line of sight. If the road is plain and you don't have any other scatter or reflector, you will have one pure reflector signal from the ground. So I have given equations for your reference, but if I simply tell you, if you walk along the road, just okay, the direct distance and the reflected distance will keep on varying. So as and when the distance is a multiple of pi, the signal will be 0. So you are not doing anything, just you are walking along the road facing towards a tower from here to here. Your signal will fluctuate up and down. That is what the two-ray tracing model says. I mean, this is applicable where you have a direct line of sight. This is, if you are standing in a highway, you can take away this model. And other ray tracing model, and just I leave it to you for your own reference. And I have given what is the coverage area. All these things are pretty simple. I have given the expression for that and what is the picture illustrating that, just for your reference then. Let me come back to this part about the compressed sensing. See, the difference between compression and compressive sensing, that should not be taken similar. In the compression, what we do, that is what typically done in image processing. You have an image, you compress that, okay, so that when you see the compressed data, you don't, you are not able to make any sense out of it. But again, you apply the decompression technique and you get the original image back. So for example, if you have to transmit a JPEG image, one image, you make the JPEG compression, send the compressed data and do the decompression, get the original image back. So that will reduce the overhead in the transmission. That is what typically compression is used for. But in compressive sensing, you have something to capture. When you are capturing, you have nothing about it. But from that, you are recovering a certain image. So that is the difference between compression and compressive sensing. While taking the measurement itself, that is nothing like this. And from nothing, you are creating something. That is what the CS compressive sensing theory says. Let us just think of one signal. For example, you have a sparse signal where you have its dimension is around 8 or 9, but you have only 2 non-zero entries in there. That is what called a sparse signal. Let us take one example. Suppose if we have a signal f of t, which has two frequency component, one at 53, another one in 531. You just apply the Fourier transform. Before apply the DFT, you have to sample the signal. So you sample it at the Nyquist state. What is a Nyquist state for the signal? Twice the rate of highest frequency. So 2 times 531. You do the sample at that rate, do the processing, you are getting the spectrum. See that even though they have both have the same amplitude, because of some processing, you get a slight difference in that, quite negligible. So that is telling you in the PSD, there is one component at 53, there is another component 531. But if you think of the spectrum, see, from 53 to 531, there is no component at all. Okay, suppose you have another signal where it is sum of sine 2 pi t, sine 2 pi 2t and so on, like up to 531. Even though if for that signal also you have to sample at the same rate, isn't it? What I'm telling, think of two signal. One has only two components, 53 and 531. Think of another signal which has all the components from 1 to 531. Okay. What about the sample rate for the another signal which has sine 2 pi t, sine 2 pi 2t and so on like that. So it is having all the 531 different component. It will also have the same Nyquist state. The signal which has only just two component, this is also having the same Nyquist state. So essentially, the another signal has a very rich content. So it is worth to spend that kind of a higher sampling rate for the signal. On the other hand, you have only two components. There is nothing between 53 and 531. Why I have to spend such a large sampling rate for the signal which has only just two frequency component? So that is what the idea of sub-Nyquist sampling. If you, there is, I am not going into the theory of it. there is a way to sample the signal even with a very smaller rate than the Nyquist rate, but still to reconstruct the signal with a reasonable approximation. So when they reconstruct a signal with the sub-Nyquist rate, we'll again able to tell you that there is one component 53, there is one component 531, but the difference is slightly larger than here. This is because of the approximation you are doing. But essentially, you are able to get some information about that. Now, why we have to study that? When you are trying to estimate a primary user, you are not interested in the primary user's actual content, right? You don't need to reconstruct it exactly. I'm not asking you what he is transmitting. I am asking you only whether he is transmitting or not, isn't it? To just tell you that whether there is a content present or not, I don't need to go for such a very accurate level, isn't it? So you are not going to decode the primary user data. That's not your job. You are just going to say that whether primary user is communicating there or not. So I want to know whether these two components are present or not. I don't worry about how much the difference is. So compared to this scheme where it is exactly or very accurately reconstructing the amplitudes with little loss of penalty on the estimate of their amplitude, I can still tell you that when there are two components at 53 and 531. So that is what the idea behind the sub-Nyquist theorem. Why we are applying that CS framework for the spectrum sensing is that in spectrum sensing, that is not my interest to decode the signal. My interest is to whether there is communication happening or not. Okay. So what are all the underlying principle of CS framework? One is that signal recovery from sub-Nyquist state sample. That we are going far below from what Nyquist actually dictating for sampling a particular signal. This CS has a wide area of application in communication technology. Including spatial multiplexing, channel estimation, and signal acquisition, and so on. And the CS framework offers a new platform for the physical layer signal processing, and that creates a new era in that technique. So what is it all about? Let me just quickly tell you one linear algebra equation. Say you have an observed linear measurement model, A is equal to Y is equal to AX plus noise. Let us don't worry about noise for the time being. Just Y is equal to AX. Y of dimension n cross 1, where A is n cross m, X is m cross 1. The question is to recover X from given Y, right? Of course, we know that A is full. Suppose A is square and full rank. Then you can put X is equal to A inverse Y, isn't it? Yeah. But A has to be having full rank and square matrix. But another case is that if A is having full column rank, then if solution exists, you will have the unique solution then. There are three cases. Okay, I think probably you might know the linear algebra and the system of linear equations. If you have a square matrix, let me quickly summarize. Say if you have a square A, full rank, then you can uniquely recover X from Y. X is equal to A inverse Y. If A is a tall matrix where it has a a number of rows is greater than number of columns, it is a tall matrix, then still unique solution exists, but it may or may not exist. You cannot guarantee for the existence, but if it exists, solution will be unique. That is what n greater than m. You have a tall matrix. If we have a fat matrix, n less than m, then there is no unique solution. That system is called underdetermined system. If you think of, suppose you have three unknowns, I have given you two equations. Can you solve it? No. You can solve it, but not with unique solution. That is what it says. Suppose you have 10 unknowns, I have given you only 5 equations. So that is equal to a fat matrix. If I have given you 10 unknowns, you need 10 equations. That is what the trivial, our conventional wisdom of linear algebra. But there are 10 unknowns, but I have given you only 5 equations. You cannot do anything. As per the theory of linear algebra and system of equations, that is an underdetermined system. There is no unique solution. Okay, this everyone knows. What's the surprise about that? CS framework tells you that unique solution is possible even n less than m, in the sense that think of a vector x 100 cross 1, but I have given you only just 10 cross 100 matrix, or I have given you only 10 equations, you can still recover the unknown vector of x 100 cross 1. Something quite surprising and against our counterintuitive our wisdom of linear algebra. But when that can happen? The unknown vector x must be sparse in the sense that even though the vector x has a large dimension, say 100 cross 1, if the number of non-zero entries in that x is very less, I can still recover that. That is one. Second part, the A, y is equal to AX, right? That matrix A is called sensing matrix in the context of CS framework. That must have certain properties. What certain property? I will come back to that. So with a sparse vector x and proper choice of A, the unique solution is guaranteed. So let me just reiterate what I have been telling you. If you have an equation with 100 size unknown vector, but I have given you only 10 equations. So A is 10 cross 100. This is 100 cross 1. Observation will be 10 cross 1. Right? What is your conventional requirement? If we have 100 cross 1 unknown vector, you need 100 observation for a square matrix. Right? So 100 unknown, 100 equations, 100 observations. That is what you need. That is what Nyquist theorem. You have 100 unknown size unknown vector. I give you only 10 equations. You have only 10 observations. This is sub-Nyquist trait. So the CS framework tells that if the unknown vector is sparse, even though the vector has a large size, but the number of non-zero entry in the vector is very, very less. That is what we have seen on example. If you think of every frequency component between 0 and 531 as the one entry, the size of the vector is 531, but it has only two non-zero entries. That is what I have been telling, right? We don't need to spend that much kind of a large sampling rate for a signal which is quite sparse in nature. Okay, where the sparsity occurs. Before that, let me tell you a few models in that. See, this is what you have y. Right now, just don't think about the psi here. Y is equal to 5 times s, for example. Then you have a large size unknown vector, but the A is fat matrix. You have only less number of observations. So given 10 cross 1 observation, you are supposed to recover 100 cross 1 unknown vector. But the 100 cross 1 unknown vector has only very few non-zero entries. By properly designing this 5 matrix, you can recover S given Y. Okay. Sometimes even the S may not be actually sparse. By making a proper linear transformation, you can make the resultant vector sparse. Let me tell you one example. You have vector X all one vector, right? Suppose this is a 128, for example, this is a 128 cross 1 vector. Say for example, you have 111, 128 ones here. If I ask you the vector is sparse, you would say no. It is not a sparse vector, isn't it? This has all values, right? So it is not sparse. Think of it, taking a DFT of it. What will happen? The DFT of a DC signal is 1 followed by all zeros, isn't it? So if you make a DFT of it, then that will become sparse. So that is why the X can be thought of an inverse DFT of another signal which is 1000. That is what I am saying. Even though underlying vector is not sparse, by properly choosing a linear transformation, you can make the vector as sparse. So that is what this in between matrix is there. So in some cases where the actual vector is not sparse, however, you may find a way to make it sparse. This is the standard model and this is like a transformed model. This is what typically we have. Sometimes you may have directly. So in this case, directly the vector is sparse. Here, after a linear transformation, that signal can be thought of as sparse vector. That is called a change of basis, if at all you have taken course in linear algebra. Okay, so what are the different models we have in that? One is the standard CS model. I think I have told you these two cases. You have a sparse vector, you have fat matrix. And another block sparse CS model. You have a big unknown vector, but the non-zero entries, they appear as a clusters or blocks. That is called a block sparse vector. Another one is that suppose you have a matrix, but instead of one observation, the same unknown vector is sampled several times. You have different observations. So that is called the multiple measurement vector model. But the different unknown vectors are having the same sparsity pattern in the sense that the non-zero values may differ, but the location of the non-zero entries are same. Such a vectors are called jointly sparse signals. One is called the sparse signal. These three are jointly sparse if they share the same sparsity pattern. Sparsity pattern is nothing but the location or indices of the non-zero entries. If the locations are same, but the values may differ, that's a different thing. But if the locations are same, then the signal is called jointly sparse signal and the model is called multiple measurement vector model. This is again the same model, but except that the sensing matrix differs for each observation. This unknown vector you sample with this sensing matrix. Another unknown vector sample with different sensing matrix. This is called generalized multiple measurement vector model. So many of the CS problems can be modeled in any one of these broad generalized broad cases. Okay. What are the, I have told you that the matrix has to have certain property. What are those properties? One property is called restricted isometry property. Okay, this equation might be looking some different to you. Let me tell you the physical meaning of this. You have a vector, you have matrix X. If you multiply a vector with this matrix, that will change the length of the vector. Isn't it? You just take any matrix A, 2 cross 2, take a vector 2 cross 1 and multiply AX. After the product, the length of the X will change, right? But if the change in the length after the multiplication, Z's norm is here, norm of the Z is here. After multiplying the matrix, the norm does not change drastically. If that is the case, it is propertying a rip of order delta. Okay, if norm remains same, delta is equal to 0. That's the point. If after multiplying the matrix, the norm of the product doesn't change with the original norm, that's it. Okay, what actually determines that change in the norm? If the eigenvalues of X are tightly packed, then the norm will not change. Let me tell you an example. What is the eigenvalues of a unit matrix, identity matrix? All ones, right? If you multiply Z with identity matrix, you will get Z only. So that is ideal case. Okay. If the eigenvalues are not spread too much, all the eigenvalues are equal to 1. So it is completely packed. So delta will be equal to 0. That is ideal case. So if you think of matrix X, Z is a vector. So what will happen? If Z is a sparse vector, so what it will do? It will multiply the corresponding non-zero entry will multiply the corresponding column in X. For example, if the first entry in Z is non-zero, that will multiply the first column of X. Z is say 100 cross 1, say 1, 10, 1, 11, 21, all the multiples of 10 are equal to non-zero entry, for example. Then it will pick up the corresponding columns from X. So if Z is a sparse vector of say sparsity 5, meaning that 5 non-zero entries are there, then this equation verifies that if you randomly take any 5 columns out of X, what about their eigenvalue? That is what the equation is testing out. You get my point? Let me repeat. You have a vector Z which is sparse. Say it is sparsity level is 5, for example, meaning that Z is that size vector 100 cross 1, but out of the 100 entry, only 5 non-zero entries are there, say for example, but the 5 can be anywhere. So if you pick any 5 columns from the X, what about their eigenvalues? That is the question about RIP. Okay, and similarly, another property is that coherence, incoherence property. Incoherence is, okay, without looking at the equation, incoherence is nothing but angle between the two vectors. So we are measuring how what about the angle between two vectors? Suppose two vectors are orthogonal, angle is equal to 90 degree. So our inner product is equal to 0. So we are measuring how far these two vectors are orthogonal to each other. What is the angle between them? The best case is 90 degree. That's what we want. Okay, I think I can quickly give you an example. Let me take 5. Dr. Kiran, can I take 5 more minutes?
Sure, sir. Up to 11:30.
Yeah, anyway, I have to give, I need to give some time for questions. Let me finish in 5 minutes. Yeah. Okay, let me take this quick example. I think yesterday I have shown you about this part, the cell search, what is the problem in interference, and why we are going for head net. All these things we discussed, right? Let me take the same example and show you one flavor of how the CS framework can be applied in this problem. Quick example. Think of a scenario. You have a mobile which is very close to the femtocell. This femtocell is, for example, say your Wi-Fi building. So I have come to your me, your Wi-Fi will not give access to me like a femtocell. So I have to connect to the faraway macro cell. In that case, the closer signal, the tower will give me a severe interference to me. So earlier we have discussed that in a conventional network, what a mobile will do, that will receive from all the towers around it and choose the one which is strongest. But here, even though this is strongest, I cannot go for it because your femtocell won't allow me to get connected with. So in this heterogeneous network, the thumb rule that always get access to the strongest received power is not always possible, right? Then what I have to do? For example, think of a mobile. It is receiving signal from two femtocell, one pico and one macro. Then these two femtocell won't give access to that. So it has to identify the cell from the pico or from the macro and choose the one, whichever is convenient or depending on other network factors. So what happens? Anytime the mobile has to identify the base stations around that. So that is what neighborhood identification problem. So that is what called neighborhood identification problem. Okay. Now, I quickly tell you about the transmission. Every base station will transmit its data in the form of frames. In every frame, there will be a dedicated training signal which is unique to the tower. Okay. Identifying the tower is equal to identifying the training signal. Identifying the training signal is equivalent to identifying the tower, because every signal is unique to every tower. Okay. So totally how many different signals can be there? There are totally 504 cells. So 504 different training signals are there. So when you randomly switch on your mobile or you enter into another circle, you have to receive the frame, locate the training signal, compute the identity of it. That will tell you the number or some information about the tower. Okay. So let me go back to the vector model directly. Suppose this is, just a minute. Yes. Come to flat. I'm in a class. Excuse me. So we have the observation Y. We have the training signal XQ1 is the signal from the identity Q1. Another signal XQ2 that is from another tower Q2 and so on. So now you have received the signal from 3 different towers Q1, Q2, Q3. Okay. These Q1, Q2, Q3 are from 1 to 504. Okay. Now this is your observation. Let me write in the matrix model like that. XQ1, XQ2, 3 are vectors. We consider flat fading, just they are multiplying by a gain factor. So these 3 are scalars, Q1, Q2, Q3, right? I think you can understand this equation from this matrix model. Now the question is, from given Y, you have to identify what is the value of Q1, Q2, Q3. And all the XQ1, XQ2, XQ3 are unique to every Q1. Identifying this equal to identifying the tower. Now, let me think of another observation. Now, let me concatenate all the possible tower cells. Say C is equal to 504 different towers are there. So I concatenate the vectors corresponding from X1, X2, X504 and think of another vector in the similar dimension, 504 cross 1 vector. Now, if you think of an example, say you have 3 towers around you. One is a number of that, say tower number 5, tower number 7 and tower number 9, for example. So the signal transmitted from the tower number 5, tower number 7 and tower number 9. So this is what you will receive from the observation, isn't it? Now let me think of all the 504 signal corresponding to 504 towers, X1, X2 up to X505, 4. Okay. Since you receive only the signal from 5, 7 and 9, only those entries are non-zero, all remaining entries are 0. So out of the 504 cross 1 vector, you have only 3 non-zero entries. Now, this vector becomes a sparse vector. Now, this is your sensing matrix. Can you control your sensing matrix? Yes, because you decide your own training signal how to design that. So, the size of the sensing matrix typically in LTE, the size of the training signal is 62. So, now you have 62 cross 504 own vector and 504 cross 1 unknown vector. But typically, even though there are 504 cells, when you randomly stand in a point, you may receive that signal from say 4 or 5 towers around you. So the vector sparsity cannot exceed 4 or 5. So the problem becomes the sparsity recovery problem in CS framework. I have given the other details, and for the flat fading LTE signal, hope these things are self-explanatory, and stop at this point to give you some time for the next session. I open to questions now. I think I am a bit fast in this session because of lack of time to cover many things. Of course, feel free to drop me an email if you want to pursue anything further. Yeah. Yeah, thanks. You can start asking your question.
Sir, there are some questions in chat box, sir. There are some questions in chat box. Shall I read out or? Shall I read out or?
Yeah. So, Dr. Hanumantarao, yes, spatial modulation with CS framework. Yeah, I can share you some reference or slides to that. Drop me an email to the email ID. Again, SM is the similar part in CS framework. We have a large unknown vector, and out of the many transmit antennas, you have only very few antennas are transmitting. So the problem is straight away a CS model.
Sorry, another question is there in the chat box. Sorry, another question is there in the chat box. How to predict primary user may use unused spectrum?
Oh, okay. Okay. Yeah, okay. I'm sorry, I didn't notice the questions prior to that. How to predict primary user to use unused spectrum? Deepa, I'm not able to catch your question clearly. Could you please elaborate? Let me just see that. How to predict primary user may use unused spectrum. Deepa, I'm not a bit clear about your question.
So already some users are using that primary spectra. Some are free, but if new user want to enter that this one, how he will know that in future that he may use and there may be interference?
Yeah, that is what I said. Once you have started your communication, you are not supposed to idle back. You have to keep on sensing again whether he is coming back or not. Suppose you have 10 megahertz bandwidth. Now I find that 0 to 1 is free. But from the same 0 to 1, any other user can come at any time. So I have to keep on sensing whether primary user is coming or not.
Oh, so the latency time of that, sir, how long that will be sensed?
Yeah, typically the sensing time is that actually takes 30% of the total frame rate. So there are several research going on how to reduce the sensing time because so much time is wasted simply to sense that.
Yes, sir. Yes, sir.
Yeah.
Okay, thank you, sir.
Yeah. So what is the time recovery? Yeah, I think I have answered that question, Dr. Nagaraj. And what is the time to detect or sense? Yeah, of course, sensing time is small. Can we use OFDM MIMO technique to transmit? Yeah, of course. See, this modulation technique is a different aspect, whether you are using OFDM, OFDMA, and so on. But to reduce the sensing time, there are several techniques like sample by sample, you come to a decision like sequential compressive sensing, like that. Just to let me type that here. You check for those terms in Google Scholar. So this is something sequential compressive sensing is that you don't dedicate one particular window for sensing. Okay, you take one window and keep on take one sample by sample and try to come to a conclusion. Once you come to a conclusion, stop it. Use the remaining portion for data. So that is what sequential sensing, rather than dedicating one portion completely for the sensing part. Because sometimes you may be able to sense quickly. So then why you have to waste that much amount of time? So that is the idea behind it. Yes, of course, Dr. Nagaraj. Yeah, as you said, because when you go for approximating, quality of signal will not quality, your quality of estimating will reduce. But that's what I said. We are not going to detect the primary user's information. Just we are trying to know whether they are there or not. Can we use SVD for sensing? No, SVD is not for sensing actually. SVD is a kind of, you can use eigenvector based sensing. There are something known as eigenspectrum sensing. So that actually there they apply SVD, but not directly. How that will work like, when there are a particular user, the eigen mode will change from the information. So they do some transformation and then identify the eigen modes that give some hint about the presence of a primary user. Yeah, so that they are not, okay, let me say that in another way, not using SVD, that is applying the concept of SVD to extending the concept of SVD to the sensing part, but not directly actually, yeah.
Sir, machine learning will be better, no, sir, for sensing the spectre. Like we can good area for research.
Actually, as I think we also discussed the same part yesterday, because when you apply machine learning or artificial intelligence, the major challenge is to get the data and identify these patterns. But this cognitive area is not yet into the market. So all these things are the theoretical level. So we can propose something in ML based approach, but when that comes to market, the biggest challenge will be getting the data. So
Yes,
for
sir,
example, you have to train that well before the time you place into the system. So to train that, you don't have enough data. Still that is not in practice. So how can we get the data for training the secondary user to get access to it?
Yes, yes.
But of course, as a line of research, we can pursue that, but that may not attract that much market value before that we get actual data and train that. Yeah, okay then. So I think I don't see any other questions. So I will share the slides, Dr. Kiran, and after appending some of the reference and so on, maybe by tomorrow evening or latest by tomorrow morning. Today evening or tomorrow morning, I will share the slides. You can share to the participants. And if any other questions, feel
Sure, sir. Thank you, sir.
Thank you, sir, for your wonderful
Yeah, so you can drop an email if you have any questions. Yeah, thank you.
Actually, it's very hard to get the resource persons in this area.
Okay. Yeah, actually, I have also bit.
In this,
Yeah, due to lack of time, I couldn't cover many things.
in this,
Some idea.
thank you very much, sir, for accepting our invitation and for enlightening us in this area. Definitely, these sessions topics orient the participants towards the research in this area. Sir, actually, participants already requested you for material. So if
Yeah,
you
yeah,
could
definitely.
send us your material. Okay, sir.
Yeah, sure.
We can share with our participants.
Yes, ma'am.
Thank you, sir. Thank you very much.
Yeah, thank you.
Thank you.
Yes, sir. Thank you so much, sir. Wonderful presentation, sir. Nice to meet you, sir. Thank you so much.
Thank you. Thank you.
Sir, very good presentation, sir. We are happy, sir, after attending this.
Yeah, sure, sure. Just some of the yesterday participants asked me some reference and so on. I have made a note of it. I would append all the text file and then compile it inside the PDF files.
Thank you.
Yeah. Okay, ma'am. Bye. See you all. Bye.
Dear participants.